All right, so it's week 5 Friday, and we are halfway through the quarter. Okay, halfway through your first quarter of your last year. I don't know what that translates to. I guess 1/6 of the way done. Okay. Well, let's. Today, I'm going to introduce Markov chains. Okay, and I'm sorry, I haven't gotten your third homework assignment posted. I will do it today. I keep saying that like every day. I'm going to do it today, and then I always want to like make little changes to enhance your learning experience, I guess. All right, but today we're going to introduce Markov chains. Okay, and a lot of times, I don't know, you hear MCMC, which is Markov Chain Monte Carlo. And it's very useful. Good stuff. But first we got to talk Markov chains before we get to Markov Chain Monte Carlo. I guess let me try to just at least motivate this a little bit. So why? Maybe I'll make this a question mark. So far we've been dealing with we introduced kind of these Bayesian concepts. We said we have Bayesian statistics, and a lot of times in order to get the answer that we want, instead of doing the integral, we can do Monte Carlo methods, all right? And if the Bayesian distribution is something that R has, that's nice, and that makes it really easy. But a lot of times it's not, and so we spent the last few weeks just talking about how to generate values from different kinds of distributions, okay? And so we had inverse CDF and rejection sampling, okay? And then as far as estimating the PDF goes, we had modifications of Monte Carlo integration and importance sampling, okay? And now I'm talking about Markov chains, okay? And so the idea is still the same, okay? Idea is we want to generate random values from a particular distribution. Okay. Now what we will see is that a lot of these methods that I've introduced, they all work in the long run, okay? But the long run, it kind of implies infinity, and we don't have infinite amount of time, right? And so, as far as rejection sampling goes, we want our envelope to be, the smallest possible m that still surrounds the target distribution, okay? But technically, you could just choose m equal to be some huge number like 1,000,000, and it'll work in the long run, but you'll just be rejecting, 99.9% of your values. And so it'll be inefficient, okay? And going along with that, we can end up in a situation, especially in higher dimensions, where the current algorithms that we have, like like rejection sampling, will be very inefficient, okay? So we want to generate random values from a particular distribution. The kind of current methods, like rejection sampling, can be very inefficient, okay? And so we might have something, for example, and I'll just write especially in high dimensions, okay? And so this might not be the best example, but let's say in one dimension we've got the normal distribution, okay? And this would be a bad idea, but let's say you decide to go from for rejection sampling. Let's say we're going to do rejection sampling. And let's say we decide to use a uniform proposal, okay? Which we know is not going to work because we would have to go off to negative infinity and plus infinity, okay? But we might say that if we go out to plus 10 and minus 10, you know, these values out here are so close to 0, I can just ignore them, okay? Because so rejection sampling, uniform proposal, maybe we'll say U comes from uniform on negative 10 to 10, okay? And then, you know, we just ignore values of z greater than 10 or more negative than or z less than negative 10, right? Because we'll say, you know, that probably never happens. Okay, and let's say, so if we do this, what proportion of values will be accepted? Okay, so so here I've got, well, I guess that we would have to figure out the m, okay? But on the normal, this is around 0.4, okay? The peak, the highest value on the normal distribution is around 0.4, the max value there. And here our height is 1 over 20, okay, or 0.05. All right, and so I'd have to kind of, m is going to have to be around 8, right? And so I will, I'm only going to accept about 12.5% of my values, okay? Something around there, okay? What if we do this in 2 dimensions? So what if I have this bivariate normal, which looks like this, right? I don't know. Okay. Can you imagine this hill and my poor drawing here? Okay. And now my uniform, like my proposal, is going to be a bivariate uniform distribution, okay? So we're going to kind of propose, we would propose 2 values, right? A coordinate of u1 and u2 coming from basically a 2-dimensional uniform on the range, you know, negative 10 to 10, okay? And if we accept about 1/8 of our values in 1 dimension, approximately what proportion of values would we accept here? About 1/64, right? So we're going to accept only assuming this is just some kind of independent thing. And as we increase the number of dimensions, the proportion of values just get lower and lower and lower and lower, okay? And so you know, all of these methods we've learned, rejection sampling is great, okay? Actually, when you use SAMP in R, it uses a rejection sampling algorithm as far as randomly selecting values from some integers and stuff. And it's really great, but in high dimensions, it can lead to a lot of values getting rejected, okay? And which will lead to inefficiency. So what Markov chains will allow us to do is it will allow us to kind of take like a little random walk inside zones of where we might sample values, okay? I'm going to first talk about Markov chains before we get into kind of the application of the Markov chain Monte Carlo. Okay, so let's just talk simple Markov chains. All right, and so we will start off with a two states. The two-state case. All right, so we will say there are two possible states for the Markov chain. A and B. Okay, so these are just random states. Either you're in state A, and so I'll draw a diagram here. Okay, or you are in state B. Okay, and we have transition probabilities. Okay, and the transition probabilities kind of describe the probability of moving from one state to another or remaining at the same state. Okay. Okay, so we will draw these with these arrows. Okay, so from A you can go to B. From A you can also remain at A. All right, if you're at B, you can transition to A, or you can remain at B. All right. I don't know. Silly example. For California, you can have, we can say A is sunny weather, and B is not sunny. Yeah. Yeah, it could be fire versus no fire. Yeah. I feel like that might be our two states, right? We have like 3 days of wet and every other day is sunny. So this will be cloudy, rain, etc. Maybe fire. Okay, and so this is, you know, your states, just some possible series. Will be A, you know, it's like every day is sunny, okay? And then maybe you get a few days of cloudiness, and then it's sunny again, and then it's, I don't know, something like this, okay? I feel like this is the month of April or something. Who knows? Okay. The idea is this series has what we call the Markov property. All right, and this means the next state depends only on the current state. Okay, the next state depends only on the current state, and or this is known as kind of the memoryless property. On your phone, you can pretend to write a text message to someone. Well, and so I think they've all updated these things, but if you pull out your phone and I don't know, you just decide to start a chat with a random person here, okay? A lot of times you'll have kind of these predictive words in the middle, right? And then you can just kind of, you can type something, right? Like if you type in hi and you hit space, it's going to kind of give you what it thinks you might say next, right? And you can just tap one of those things, and it might say like hi, I, and then as soon as I tap I, it gives me 3 new predictions, right? And it's going to be so for me, I typed in I, and then and I have 3 words: was, am, and have. Okay, and those all sound like those are highly probable words to follow the word I. Okay, so I'm going to just say was, and then and Google has like learned my speech patterns. Okay, so after I type in was, it says the next 3 things are just, or wondering, or interested, right? So you know, my sentence would be like, hi, I was interested, I was wondering, or hi, I was just blah 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 blah. And I think they've adapted them so they are no longer Markov, where like it's going to take into account like the previous maybe 2 or 3 words, okay? But it's kind of the idea of you put one word in, and it's going to kind of give you like what it thinks you might say in the next, what the next word is that you're going to type out, okay? So, you know, the next state depends only on the current state. I think the modern predictive keyboards now take into account a few more than just one state. But if it only takes into account one state, that means where you are today, then we will have a Markov chain, okay? So, you know, what happened yesterday doesn't matter. It's just where are we today, okay? All right, so we write down our transition probabilities in a transition matrix, okay? All right, and this will be kind of current. And currently you can be at states A or B, and then we'll have kind of next. And next you can be at A or B. Okay? And so if you are currently, I'm just going to make up some numbers, but if you're currently at A, then we're going to say there's a 70% chance of remaining at A, or 30% chance of transitioning to B. And if you are at B, we're going to say maybe there's a 40% chance of switching to A, and a 60% chance of remaining at B. So I guess in both cases, the states kind of favor staying at themselves, but you have a higher chance of going from B to A than you do from going from A to B. Okay. So this is basically saying, you know, if today is A, the probability tomorrow is A is 0.7. Okay. And I guess depending on the textbooks and stuff, they might write them the other way. The way I have it written, the row sums must be 1, okay? Okay. And so we'll have A and B. And so our diagram looks like this. Okay. And we will say a chain, or a chain is irreducible if you can reach all other states from any other state. Okay, so in this case, you can, from A you can go to B, and from B you can go to A, so this chain is irreducible. Okay, you could have you can have a series of states, A, B, C. Okay. All right, and this is also irreducible. Okay. A chain is irreducible if you can reach any other state, all other states from any other state. Maybe I will say eventually. Okay, so there's no direct path from A to B, okay, but you can get there by going from A to C and then from C to B. Okay, so that's fine. Okay, but if you have something like okay, this will be not irreducible. Okay, I mean, even if you have something like this. Okay, so if you're at D, there's no way to reach A. Okay, no path from D to A or B. Okay. So these are just kind of some definitions here. So this is our transition matrix. This is what it looks like. This chain is irreducible. There's also another idea that's going to be important, and this is called periodic. I'm sorry, aperiodic. Or I don't know, periodic, aperiodic. All right. Okay, and this means we're going to say a Markov chain is aperiodic if, well, okay. It's going to be better if I start off with the definition of periodic. All right, so we'll say periodic, a Markov chain is periodic if certain states are possible only on certain intervals or periods. Okay, so if you have this is going to be periodic, okay, because it's going to go A, B, A, B, A, B, right? So A happens on kind of the odd beats. and B happens on the even, I should say, intervals. Okay, and then aperiodic is going to be the opposite of that, right? So if we have this, then this becomes aperiodic, because then I can go A, B, A, B, A, or something, or A, B, you know, A, however you want it, right? So there's no... So once the chain gets going, there's no requirement that B can only happen on certain intervals, okay? So kind of practically speaking, if it is possible to go from one state back to itself, the chain becomes aperiodic. Okay. Even if the rest of the chain, like if you were to take away that one thing where it goes back to itself, and the rest of the chain is periodic, okay, as soon as you have something kind of able to go back to itself, then it becomes aperiodic, because you can kind of go back to yourself and take like this rest beat and throw everything else off. Okay, so I mentioned these things because there's this theorem that says if a Markov chain is irreducible and aperiodic, then given enough time, it will, the states that it produces will follow a stationary distribution, okay? The ergodic theorem. This is a very like informal definition, okay? You can go on Wikipedia and look up Markov chains and ergodic theorem and stuff, and it's a lot more formal, okay? But big picture idea, the idea is if a chain is irreducible and aperiodic, then the chain will eventually converge to a, quote, stationary distribution. Okay, and what this means is that the states that are produced by the chain will follow a given probability distribution. Right. It's, you know, Markov chains are what we consider stochastic processes, meaning it's subject to randomness. So if you try to predict any one individual state, it's not possible, okay? However, if you just look, but we are able to describe kind of the distribution of states that it produces. That overall, it's going to produce, you know, this value with this probability and this state with this probability and things like that, okay? So just like any other random distribution, you cannot predict the next value it's going to produce, but we can model or we can describe kind of the overall distribution of values it will produce, right? So Markov chains are stochastic, that is subject to randomness. Okay, so we cannot predict individual values, but we can describe the distribution. Distribution of values it produces. Okay, so the stationary distribution is the distribution of the quote system at equilibrium. Equilibrium. Okay, I think I spelled that right. Or another way to say it is that you know, and for the two-state process, it means the proportion going from A to B is equal to the proportion going from B to A. Okay, so let's just kind of take a look at our two-state case, right? So I've got A and I've got B. So we have this. What are my numbers again? I put 0.3, 0.7. B to A is 0.4, and this is 0.6, okay? And so my transition matrix, so this is next, this is current. I'm going to just write it this way, is 0.7, 0.3, and 0.4 and 0.6. Okay, so not at equilibrium. Would be kind of, so not at equilibrium example, we'll say everyone is at A. Okay, so our current distribution is 1, 0, okay? And then I can multiply this by our transition matrix, okay? Okay, And basically, the result will be what? Okay, we're going to say everyone at A. So everyone's at A, and of those at A, 0.7 are going to remain at A. And then, and there's no one at B, so none of the 0.4 of the 0 will go to A, okay? And then over here, and those at A, everyone's at A, and 0.3 of those will go to B. And so the resulting distribution is going to be this, okay? So this is after one iteration. This is our distribution. Okay. Now I can multiply this by our transition matrix again, which I will write 0.7, 0.3, 0.4, and 0.6. Okay. All right, and so what we have now, okay, is we've got 70% of the people are at A. All right, so I'll kind of, so I'm going to just break this up. So this will be A to A is going to be, we got 70% of the people at A, and of those 70% of that 70% will go to A, and that's 0.49. And then we also have some people who are at B. 30% of people are at B, and of those, 40% will transition to A. Okay, so total A, total going to A, will be 0.61. And then I guess I can do the same thing for B, okay? I know. Because they have to add up to 1, right? But it's going to be A, from going from A to B, you got 70% currently at A, and of those, 30% will go to B. And then we've got 30% at B, and of those, 60% of them will go to A, will remain at B. Okay, so that's going to add up. Total to B is going to be 0.39. Okay, and that makes sense because yeah, the total distribution has to add up to 1. Okay, so these states are not at equilibrium because every time I multiply it by the transition matrix, I get something different, okay? What we want is a matrix, or we want the distribution so that if I multiply the distribution by the transition matrix, we're going to get back the same distribution, okay? And we'll call this pi, okay? I don't know why it's called pi, but it's such that if we do pi times the transition matrix, we're going to get pi back, okay? Pi is a, row vector. That sums to 1, okay? And you can kind of specify this as pi a and pi b, and you have the condition that pi a plus pi b have to add up to 1. Okay, and then what you want is you multiply it by your transition matrix. And what you will get is 0.7 pi a plus 0.4 pi b. And over here we have 0.3 pi a plus 0.6 pi b. Okay, And you set these equal to each other. You say pi a has to equal this. And then pi b has to equal this. Okay, and then you have this constraint because right now there's currently infinitely many values, so the constraint means there's only going to be one, okay, where it's going to work. And okay, so anyway, the solution is going to be 4/7 and 3/7, okay? And we can see if I do this, so I mean, so given any transition matrix, you should be able to solve this, right? Okay. It gets more complicated if you have more than two states, but anyway, if we do this, we would get 0.7 times 4/7 plus what? I can't. Why are my eyes messing up on me? Okay, 0.4 times 3/7. And we will see that indeed this is right, 4/7. Okay, this will add up to 4/7. And then and if I do the other one, and I do 0.3 times 4/7 plus 0.6 times 3/7, this will be 0.12, and 0.6 times 3 is 0.18. Or 1.8, I'm sorry, 1.2 and 1.8, and that adds up to 3/7 as well, okay? So we have achieved stationarity. All right. Does this look kind of familiar, where I have, I've got a vector times a matrix equals a vector? Equals, I'll say the same vector. Because that's what we have, right? So we had, this is what we said for the stationary distribution. We said we've got a vector, the stationary distribution is pi, okay, and we multiplied it by the transition matrix. And we get back the same vector pi. Does that form look kind of familiar? Okay. What does it look familiar to? What's that? Eigenvectors, right? So eigenvectors, we say you've got some matrix A times, what's the traditional vector that we use? A times X? What? A times V? Okay, so you've got A times V is equal to lambda V, right? So you've got some kind of, so you have matrix times vector, and then now we're just going to have lambda is 1, okay, some scalar times the vector. Okay, so because the vector's on the flip side of this, it turns out that the stationary distribution will be proportional to the eigenvectors of the transpose of the transition matrix, okay? Proportional to the eigenvector of the transpose of the transition matrix, okay? So that when you take a vector and you multiply it by the matrix, you get basically its, get the value back itself, okay? It's gonna have to be, so the matrix will have kind of two eigenvectors. If it's a 2 by 2 matrix, it's gonna have two eigenvectors, but only one of them will have all positive or all negative values, okay? So the other one will kind of be mixed. One will be positive and one will be negative. That will not work for a stationary distribution, okay? Only one will be all positive, okay? But the signs of the eigenvectors are arbitrary, so they could also be all negative, okay? A 2 by 2 matrix will have two eigenvectors. And one will be basically all positive or all negative. And then the other will be mixed. One positive and one negative. Okay, and so pi will be proportional to this one. Okay, we'll stop there for today, and then we'll start applying this to generating values from some random distribution.